Welcome back to this sixth lecture on bio micro electromechanical systems. We would like to review what we did last time. Last time we talked about electrochemical half cells, and we also discussed about how to maintain continuity of the reduction oxidation process. If you remember, there was a lump of zinc which we put in a copper sulphate solution, and immediately it would be covered with metallic copper, after which there will not be any reaction any further. And in order to maintain the continuity, we basically tried to connect two half cells, one where zinc was in zinc a salt solution of zinc, and copper was independently in another salt solution of copper, and then we connected both the solutions externally through a salt bridge and both the electrodes with the conduit. And basically that kind of was useful in maintaining a continuous flow of electrons, and therefore generated an EMF and a current. We also talked about electroactivity of species, basically the ability of a particular metal to displace hydrogen from water, steam or acid, and essentially this is a very important aspect of electrochemistry, because we kind of know an order in which what would displace what from its corresponding salt solution. We also talked about relative and absolute potentials, and we discussed the standard hydrogen electrode, which is essentially a platinum electrode dipped in a 1 molar HCl solution in water, thus forming hydronium ions H3O plus, where hydrogen was bubbled through at about 1 atmosphere pressure, and the temperature was maintained at about 25 degrees Celsius or so. So then we started just about calculating cell potentials, and there the main question that needs to be addressed is how can we really have an idea or a relationship between the concentration of an analyte and the EMF that it would generate. And so for that we will be actually deriving something which we have commonly known as the Nernst equation. So let me look through how this derivation is done. I would typically like to derive this through the fundamental principles of chemistry, and then go ahead with utilizing this Nernst equation to calculate the concentrations of different analytes of interest. So in order to start with, we really need to find out what is the total work done by an electrochemical cell that we have discussed yesterday. So as we know, there is a potential difference between the anode and the cathode, and anode is essentially where the oxidation reaction happens, the cathode is where the reduction reaction happens, and due to this potential difference and owing to this difference, there is a flow of charge across the circuit from the cathode from the anode to the cathode. There is an electron flow, and correspondingly there is a you can say that the conventional current direction is from the cathode to the anode. So there is work essentially which the cell does in order to transfer some electrons from one electrode to other, and the amount of electrical energy that is essentially spent during this operation of an electrochemical cell is, I am sorry, let me just go ahead and give me a minute. So essentially when we talk about work done from by an electrochemical cell during this operation of charge transfer, the chemical energy which is stored in form of the salt solution with the particular metal is transformed into electrical energy, okay, and the total amount of electrical energy in this process is E dash cell into C trans, where C trans is the total charge that is transferred from one electrode to another, and E dash cell is the differential cell potential between both the electrodes. So we can also express this in a little different manner by assuming that n number of moles of electrons have really crossed from one electrode to another, and essentially there is this famous Faraday constant which is corresponding to the charge of 1 mole of electron. So as we all know that the electronic charge is around 1.6 into 10 to the power of minus 19 coulomb, and if you multiply this with 1 mole, the Avogadro number, 6.033 10 to the power of 23, you get this 96,485 coulomb. So, essentially this value is the charge for 1 mole electrons. So, if you have n mole electrons which are crossing from one electrode to another, the C trans, which is the total amount of charge so crossed, is also known as, also given as NF, okay. And this is a negative charge. So, you have a negative sign which comes up. So, this charge is transferred under a potential E dash cell, and that is essentially what the maximum work done is of this system, okay. So, this electrochemical cell essentially in the process of a charge transfer of NF value under a cell potential E dash cell makes or contributes a maximum work given by minus NF E dash cell. So, from the principles of thermodynamics, we also know this very famous Gibbs free energy concept, which is essentially the maximum energy that can be extracted from a system, and that can be equated to the maximum work done by the system. So, really the Gibbs free energy delta G, which is also given by this expression here minus RT ln K, and K is the equilibrium constant, which I am going to come in just about a little bit, and this essentially this expression comes from the Van 't Hoff equation. We will just do this in a little bit, but what I am trying to say here is that delta G of any free cell, the free energy of any free cell, is also equal to the maximum work that can be done by the free cell. So, delta G is minus NF E dash cell, and is also can be represented as minus RT ln K, okay. So, let us look at the Van 't Hoff equation and how it came from thermodynamics. So, the Van 't Hoff for the first time observed that there is a linear relationship between the natural log of the rate of a reaction and the inverse of temperature. And the rate of a reaction, again assuming this to be the reaction, alpha moles of A reacts with beta moles of B to and with several other components here reversibly to obtain sigma moles of S, tau mole of T, and several other products here. So, by the Le Chatelier's principle, you can really find out the rate constant of any such reaction, okay. And what this principle says is that the rate constant of any forward reaction is proportional to the product of the activity of the products raised to their stoichiometric coefficients. The stoichiometric coefficients here being alpha, as you see here in this, beta, so how many moles are participating, and sigma and tau, okay. So, this is what the stoichiometric coefficients of this different reactions are. And so, therefore, Le Chatelier's principle says that the rate constant of any forward reaction is proportional to the product of the activity of the of the products raised to their stoichiometric coefficient. So, here I am just about to explain in a little bit what activity really means. At this time, let us just consider it to be equal to the concentration, okay. So, activity essentially is a term which is a factor of the concentration of a particular analyte, and I will be explaining this in a great details later, because for designing electrodes which would be able to do electrochemical sensing in biomems devices, we need to find out sometimes the activity of an ion of interest rather than the concentration of the ion of interest. So, essentially by the Le Chatelier's principle, the rate constant of any forward reaction is proportional to the product of the activity of the products. That means S and T here are the products of the reaction, right, and it is a multiplication or a product of the activity of S and T, that means the products of the reaction raised to power their stoichiometric coefficient sigma and tau and the others, and divided by the activity of the reactants of this particular reaction raised to power their stoichiometric coefficients, which is alpha and beta, okay. So, for any general chemical reaction, this is how the equilibrium constant or the rate constant of a particular reaction can be found out. And so, this is what is a critical parameter to study any redox reaction, reduction oxidation reaction, and essentially the change in one, like let us say the change in the reactant side would essentially lead to a shift in the equilibrium, and there would be an increase in the forward rate. And so what would happen is that more of A would be converted into S or T, and therefore the equilibrium will shift back to its normal. So any disturbance on any side in terms of concentrations of the reactants or the products would lead to a shift of the equilibrium position, and this equilibrium would try to get back to normalcy. That is how these redox couples really work. Okay. So in the solutions of high ionic strength, the activity coefficient is by and large constant, and the activity of the product changes to the concentration. So we really bother about those situations where the ionic strength may not be very huge, and that is really the case in some of the samples of interest or the analytes of interest that we try to measure using bio-MEMS architecture. Okay, because this ionic strength is sometimes not under control, and therefore how do we really measure very accurately the EMF and correlate that to the concentration of an analyte which has a low ionic strength is the challenge. And for that there are certain rules and protocols which are followed, so that in an in vitro sense we can make a repeatable measurement and correlate the EMF of such a product or of such a reaction to the concentration of one of the analytes of interest. So what essentially Van 't Hoff did is he plotted experimentally the rate constants, the natural log of the rate constant ln k, okay, of some of these reactions in the gas phase typically with an inverse of temperature. Okay. And what he found out that there is really a linear fit between the inverse of temperature and the natural log of the rate constant k, as has been indicated by or as has been calculated from the Le Chatelier's principle. Okay. So as there is a linear fit, you could express the two parameters here in question, the x and y, in the form y equal to mx plus c. The question is what m and c would look like. So from several experimental results, what he obtained is that if we consider x to be 1 by t and y to be the natural log of the rate constant k, then the slope m of such in such a situation was also the minus change in, or it was the negative of the change in enthalpy per unit the Rydberg's constant r, and the intercept c in such a case, in most of the cases, was also the change in entropy of this particular reaction per unit the Rydberg's constant r. And so these are actually experimental results, and in most of these cases, in all these different equilibrium situations of different reactants and products, he obtained an uniquely similar kind of behavior where he could find out, or he could generalize, that for this situation the slope and the intercept are minus h by r, Rydberg's constant, and minus and delta s, the change in entropy of the reaction per unit the Rydberg's constant. Okay. So also from thermodynamics, if we consider the Gibbs free energy, it is given by a relationship between the enthalpy and the total entropy of the system as delta H minus T delta S. So if we substitute for H in this particular reaction, let us say we want to substitute for delta H from 1. So delta H would be also represented as RT ln k minus T delta S, and so delta H theta can be represented as T delta S theta minus RT ln k. Okay. So let us say this equation is another representation of 1, and it can be represented as 3. So if we put this 3 to find out what really the delta G value would be from equation 2, then delta G theta can be represented as T delta S theta minus R T ln k minus T delta S theta. Sorry. And essentially therefore, the delta J theta can be represented as minus R T ln k. Okay. So, if we consider this to be equation number 4 and try to find out if there is a relationship between the NF E cell and this R T ln k from the Van Hoff's equation, we get a very simple relationship which is the foundation for Nernst equation. Okay. So, essentially we can say from we can write the equation 4 again here in more simpler terms. So, the free energy delta G, which was also earlier defined as minus NF E cell, where N is the number of moles of electrons flown between both electrodes, and F is the Faraday constant (96,500) coulomb per mole, charge of 1 mole electron, and E cell equals the potential difference between both the electrodes. So, essentially delta G also can be expressed as minus R T ln k from the Van Hoff equation, remember equation number 4. Okay. So, therefore, delta G, which is equal to minus R T ln k, can be represented as minus NF E cell. So, here is a little problem, because what will happen if the equilibrium constant k equals unity or 1, right. So, essentially ln of 1, as we know, is 0, and therefore there will not be any free energy of the system which is available, and this is a major problem which one faces. And so, therefore, we have to develop a strategy where we can take care of this equation, so that in the equation itself. So, basically just this equation has to have a scheme to accommodate this problem, that what happens when the k value is unity. And so, basically what this equation can be modified as is that, let us assume that there is a certain G value known as delta G 0, where in situations when the k value becomes unity, right. And then we assume that this corresponds to a value of E cell E0 cell charge, right. So, essentially then this delta G equation gets modified to delta G 0 minus R T ln k. In this case, even if k is unity, the delta G value is equated to delta G 0, and this delta G 0 can be converted or can be thought of as the movement of NF charges across both the electrodes at a potential difference E 0 cell, and therefore this is essentially the final form of what we call or what we know as the Nernst equation. So, delta G is again N minus NF E cell from the earlier derivation, and it is equated to minus NF E naught cell, that means the corresponding potential when the reactants are all 1 molar in concentration. K, mind you, comes equal to 1, and one of the cases is that when all these different activities that we have been considering of A, B, S and T come out to be equal to all unity. Okay. So, essentially the NFE cell minus NFE cell can be equated to minus NF E naught cell minus RT ln K, and this is what the final form of Nernst equation will look like. So, we can calculate the E cell value by just looking at E naught cell and this term here RT by NF ln of K. E naught cell again is the cell potential when all the concentrations of so called reactants and products are unity. Concentration of reactants and products are unity when E cell becomes E naught cell. Okay. So, that is essentially what the Nernst equation is all about. So, now it is a very interesting thing that comes up, that you can really equate the EMF, the potential of such a system, to the concentration of the reactants and the products, and that is again what our goal is in all sensing, that if analytes of interest and the concentrations of analytes of interest can be detected by looking at their EMF values of the particular cell. Okay. So, let us do a little bit of post calculation onto this equation. There are two aspects which I would like to mention here. One is that let us think that in a reaction a certain reactant R is getting converted or oxidized into species OX and giving an electron, right. So, in such a reaction, the rate of reaction can be written as the activity of OX to the power its stoichiometric coefficient, which is 1 in this case, divided by activity of R, the material that is getting oxidized, to the power of its own stoichiometric coefficient, which is 1 in this case. And so, therefore, K can be written down as the activity OX by activity R. In case of the EMFs, if you look at the EMF E cell and Nernst equation, it comes out to be E 0 cell by this equation plus RT by NF natural log of K, and K is activity of OX by activity of R. Okay. And essentially, when you are considering a case where there is a metal electrode and its corresponding salt solution, we can safely assume the activity of the metal as unity. Okay. So, because it does not have its own ionic state in the solution in any case, it is fixed, and it gives ions though, and those ions have a certain activity AOX. Okay. So, in that case the Nernst equation would change to E cell equal to E 0 cell plus RT by NF ln AOX, okay, because the AR is unity in this case. Let us also look at if we can do something about this RT by NF. If we assume that the whole reaction takes place at room temperature and standard conditions, which is 25 degrees Celsius, and if we take the value of R to be 8.314 joule per Kelvin mole, the value of F Faraday constant to be 96,480 coulomb per mole, T at 25 degrees Celsius means 298 Kelvin. Therefore, we can calculate the RT by NF as 0.06 by N. Okay. And so, therefore, in the Nernst slope, of the E cell really comes out to be 0.06 by N. So, if you plot the E cell with the logarithm of the oxidant, the concentration of the ion, which is also proportional to the concentration of the analyte of interest in some cases where the analyte is getting oxidized, then the E cell and the concentration are really in terms of a linear equation. Okay. And that is the beauty, that the slope of that equation is also inversely proportional to the number of moles of charge transfer that is taking place, and the intercept of that equation is essentially this E0 cell factor. Okay. So, let us now look at some practical electrode design problems, and from this essentially we will move on to the corresponding MEMS modules of electrodes, which would essentially use the same principles of electrochemistry, but then they will have to be considered on because of their miniaturized size. There have to be other aspects like, you know, ionic strength, or the concentration of the ion of interest, or whether there are any competing ions in that such a solution which formulates you know, a major paradigm for designing such electrodes. So, let us look at this this half cell combined to a reference electrode, and if you look at, let's just look at the drawing here first to begin with. So, you have you know, some kind of a reference electrode with respect to which you would like to measure the interaction between the metal getting into the solution as the oxidized metal Mn plus. Okay. The reference electrode here is essentially nothing but a glass capillary which is covered by this liquid junction, and this develops a potential, let us assume ELJ with respect to the solution, and inside this glass capillary we have this electrolyte which is very standardized, and it has a standard concentration, and it has a sensing reference electrode here which goes into the electrolyte. So, any charge transfer that is taking place is through this liquid junction and through the electrolyte which is inside the capillary, and then goes on to this conduit, this wire here as you can see, and this essentially formulates an EMF here because of this configuration, and can be the reference electrode with respect to which you measure the activity of a metal and a solution like this. Okay. So, if we look at if we really connect these two, you know, externally, let us say we are trying to measure by connecting these two externally using a voltmeter. Give me 1 minute. Okay. So, let us say we are just trying to connect these two electrodes externally using a voltage measuring device. So, in that case the E cell in this particular configuration can be written down as the E dash metal to metallic ion conversion, M to Mn plus conversion. So, the potential of this interaction between metal and the metal solution or the salt solution of the metal minus the E reference potential, which is at this point E REF, minus again the liquid junction potential, which is again contributing to the ion exchange process between the external solution and the internal solution. Okay. And so, from the Nernst equation, as you know already, if we consider the activity of the metal here to be equal to unity, E dash cell in that case, or E dash of this oxidation, or the EMF produced by this oxidation reaction, can be written down as the E0 dash this oxidation reaction corresponding to the case when the reaction rate is unity, or the rate constant K is unity, plus the Nernstian slope S 0.06 by n log of Mn plus the concentration of the oxidant. Okay. And essentially if so the E cell can be represented as this particular value here, which is E dash 0 plus S log of Mn plus oxidant minus E reference minus E Lj. So we can actually pull this together and make this under the same bracket as E dash 0 minus E reference minus Eij and plus S times of log concentration of Mn plus, and this is essentially a straight line. Okay. So if you plot the E cell value here, give me 1 minute, let me okay. So if you plot the E cell value, let us say we plot it somewhere here with respect to the concentration of the oxidant Mn plus, right, you get a straight line from this particular equation, y, which is E cell, equal to mx, m being the slope S, plus c, which is E dash 0 minus E reference minus Ij. We assume this to be k, let us suppose, and this to be slope m. So this here is really what this slope k is, or this intercept k is, and the slope of the straight line is S. So therefore again this EMF and concentration shows a strange linearity. All right. So the next point which I would like to emphasize is that really if you look at the solution on a very close basis, there is a lot of other activity which is going on inside the solution. Okay. And the concentration of an ion is really very diffused, because there are so many other ion to ion attractions or interactions which are happening that really can we say that the ion of interest that we are looking at has exactly the same effect in the charge transfer process as its concentration. Okay. So therefore it is pertinent to describe a term which can give an idea of what happens when this small ion is interacting with several other competing ions. There are forces of attraction, repulsion, there is a change in its overall state. There are so many counter ions which are there in the solution. Let us say we are detecting a calcium plus 2 or positive calcium ion. So there are a lot of, let us say, chlorine ions around it. So there are, these are counter ions. So there are ion clouds, and there are this this central ion of interest. So the activity of an ion is the corresponding the corresponding factor, the corresponding term which can give an idea of the interactions between ions, both electrostatic and covalent. Okay. So the ionic activity can be defined as of an ion can be defined as the result of the interactions between ions, both electrostatic and covalent, and the activity of an ion is influenced by its surroundings. And so if suppose the ion is in a cage of water molecules, it may have a different activity factor than when it is in the middle of the counter ion cloud. Okay. And in most electrochemistry, the activity of the surrounding non-interfering ions is kept very high, so that the target ions are able to get detected in trace concentrations and also do not easily get affected by their own interactions. So, this is something very very critical to be observed, that in situations where you have several competing ions, the best way to reduce the interaction between these competing ions is to create a high ionic background, okay. And essentially you create something, some ions or something which is having an ionic state, but it is non interfering with the ions of interest. So, if such a kind of situation happens, then you can by and large create a huge background, so that these interactions between the competing ions become very very small or insignificant. In that case, the ionic activity, which is the more appropriate term giving an idea of the electronic interactions, can be described as the activity coefficient, and this is a constant, terms the concentration of the particular ion of interest. Now, this activity coefficient can be depending on different situations, it can have different values, where sometimes the ionic activity can be too high, sometimes it can be too low. And if the idea is that if you have a surrounding non interfering heavy ion cloud around the target ion, it kind of gets equal to the concentration of the ion, and you can easily get to detect the exact quantity of the target ion of interest, okay. And so therefore, especially in MEMS kind of protocols, where we are talking about selecting over a very small over a very small volume of liquid, there is always almost always a tendency of the activity to be very much different than the concentration. And so we are next going to find out how it is possible by designing an electrode to pick up a certain ion over, let us say, several competing ions, and that is how we get into the field of ion selective electrode. Okay, so basically let us do a little bit a small problem on finding out the EMF before going into the ion selective electrodes. So, in this example there is a galvanic cell which consists of a standard hydrogen electrode and a rod of zinc dipping into a solution of zinc ions at 298 Kelvin, and if it gives a measured EMF of minus 0.789 volts, find out the activity of the zinc ions. So, we apply the Nernst equation here, and essentially the E cell in this case can be represented as the E0 cell plus the Nernstian slope 0.06 divided by N in this case, because it is a zinc getting oxidized into Zn plus 2 and 2 electrons, the N equals actually 2 in this case, okay, and into log of the activity of zinc plus 2 ions, okay. So, if we it is written, I mean, or it is given in the problem that the EMF E of this particular cell is minus 0.789 volts, okay, and with respect to this is with respect to a standard hydrogen electrode. So, the E0 the standard potential with respect to that electrode from the tables which I have described in my earlier lecture comes out to be 0.76 volts, okay. So, this is essentially the half cell potential. If you remember, we had discussed a table wherein all these half cell potentials were found out by connecting the respective cell to a standard hydrogen electrode. So, from this equation, therefore, substituting the values of E and E0 and n equal to 2, we obtain the log of the activity of Zn as 2 times of minus 0.789 minus of minus 0.76 divided by 0.06, okay, and the activity of zinc comes out to be equal to 0.1 molar. So, the activity of the zinc ions in this particular example is around 0.1 molar. It may happen the concentration of the zinc ions is a little more, but due to the shielding effect the activity may be a little less. Okay. So, now let us look at what these ion selective electrodes are or what they do. Okay. So, we are very often faced with the problem of detection where there are more than one competing ions in a particular solution, okay. And in that case we want to find out a particular ion in an analyte of interest. So, essentially the ion selective electrode is a transducer which converts the activity of a specific ion of interest, okay, dissolved in a solution into an electric potential. So, even though there are more than one such ions in the solution and the ion of interest has to be specifically reported using an ion selective electrode. Okay. So, the basic setup of an ion selective electrode can be represented here in this particular figure, and if you look at the setup you can see that there are two electrodes. One is the reference electrode which is made in a similar manner with a capillary and essentially a liquid junction, okay, like any reference electrode would make, and an electrode immersed inside a solution of standard or known concentration of ions, okay. And the ion selective electrode essentially is a kind of copy of the same with an exception that instead of the liquid junction you now have a membrane here which is selective to an ion of interest. So, therefore, this membrane is designed in a manner that it can take up only a few ions of interest from the solution which this membrane is designed to take up, and therefore, this whole assembly is immersed inside the analyte of interest, and the potential is found out, the potential difference is found out between the reference and the ion selective electrode, okay. And so, therefore, we can say that it can specifically, the job of it is to specifically select one particular ion over a range of different ions. Suitable examples are pH electrodes, okay, and just picking up hydrogen ions. So, the pH electrode picks up only hydrogen ions and leaves the other ones behind. So, therefore, that is an ion selective electrode, okay. So, the basic ISE setup includes a meter, a probe, okay, selective to each analyte, and the selection is done by using this small membrane here, and essentially it also uses various consumables used for pH or ionic strength adjustments, okay. This is important because you want to create a large background of ions so that you can pick up an ion of interest in that background, all right. So, the interaction of that particular ion of interest with the other ions surrounding it are eliminated by the strong interaction forces offered by the background in general, but again, as the background ions are non-interfering in nature, they would really not contribute to any charge transfer process. The only charge transfer would come due to the particular ion of interest, okay. So, an ion selective electrode essentially is based on the measurement of the potential generated across a membrane here, a selective membrane here. The membrane is usually attached to the end of this tube, and essentially there is a solution here for internal reference of this particular electrode, and the whole assembly is immersed into the analyte for the measurement purpose. Let us talk a little bit more about what these membranes are or what they are supposed to do, okay. So, the basic property that is imparted onto the ion selective electrode is by virtue of the membrane, okay. And so, the membrane should have some characteristic of some feature maybe if it is a network of pores which might match to a certain ion size, it might be able to pick up a certain ion over the n number of other competing or interfering ions. So, there is a size based selection in that case. It could also be made up of some biological material which can recognize only a certain ion or a certain group of ions of interest. Okay. So, essentially there are several different kind of ion exchange membranes that are available for designing ion selective electrodes. Let us look at these one by one. So, there are these glassy membranes which are made from an ion exchange type of glass. Okay. And they are typically the silicates of chalcogenide metals. Chalcogenide, if you just recall from the group 6 of the periodic table, are sulfur, selenium or tellurium. These are also known as the chalcogenides, okay, the group 6 elements of the periodic table. So, essentially the silicates of such metals form excellent ion exchange type of glassy materials. So, they are covalently bonded materials. So, you can think of the entire glass matrix as an infinitely bonded molecule. Okay. So, it is one bonded molecule with in between spurts of these sulfur, selenium, tellurium, these kind of metals. So, such glasses have the tendency by maybe the virtue of their crystal structures to show high selectivity for single charged cations. Okay. So, ions like let us say hydrogen plus, sodium, Na plus, silver, or some at the most some double charged metal ions such as let us say lead and cadmium ions. So, these glasses show a strange tendency of just adhering to a certain size with a single charge and a certain size with a double charge. So, that is why it is probably related something to do with the crystal structure of these covalently bonded silicates of chalcogenide. Okay. The other type of ion exchange membranes are crystalline membranes, and one example that I can quote is the lanthanum fluoride crystal for fluorine ions. Okay. So, essentially this is a size based selection again. So, these contain mono or polycrystallites of single substances. Only those ions which can introduce themselves within the crystal are selected by virtue of the membrane being formed by this crystalline material. So, these are some of the various types of ion exchange membranes that are available. Some more could be these ion exchange resin membranes. These are very interesting in nature. So, there is a compound called valinomycin, okay, which is normally available in the cell membranes of streptomyces, and essentially the purpose of such a compound is to give way to exocytotic processes of exchange of potassium and calcium ions between the periplasm and the cytoplasm of a certain cell. Okay. So, therefore, if such kind of materials can be again enclosed or entrapped inside a polymeric material or a polymeric resin, it can form an excellent source of selection of let us say potassium or calcium, just as it happens naturally in case of cell by virtue of opening and closing of ion channels inside the artificial membrane that you make using these. So, the whole idea here is that valinomycin, which is also an organic extract, especially it is a natural extract, you can say, can be used for the same application that it is used for naturally. Okay. And this can be a fantastic ion selective electrode. Another type of ion exchange membrane is really enzyme electrodes, although these are really more related to the overall selectivity of an analyte of interest. Okay. So, what happens that in such an electrode there is an enzyme which would react to only a particular substrate. So, the whole purpose of sensing or a detection is to detect one particular species over the other competing species, right. So, in this case the particular enzyme may just react to the species of interest. Say for example, in glucose, as I have mentioned earlier quite a number of times, this glucose oxidase enzyme would oxygenate glucose and break it into gluconic acid and hydrogen peroxide, and therefore this is again giving a selectivity aspect to the sensing mechanism. Okay. Hydrogen peroxide can be measured by a pH electrode, of course, which has some other ion selective membrane, which can maybe some glass of chalcogenide, which can easily take up the hydrogen plus ions over the other competing ion. Okay. So, that in a nutshell what the ion selective electrodes are. How are they constructed? So, essentially the electrodes are prepared from a glass capillary tubing, and the resin material in most of these is polyvinyl chloride PVC, okay, which is dissolved in a solvent and added with some plasticizers. I would just like to recall that plasticizers give this unique ability of the polymer to flow more, by getting into the chains of a polymer and make the chains roll over more easily. So, you add some plasticizers for making it more fluidic in nature, okay, especially when they are in the liquid form before they cure. And so therefore, this particular ion specific material, whatever you have to design is added to this particular solution, and then this capillary is dipped into the solution, and the solution gets into the end and forms a small plug, okay, and plug is provided a certain ion certain strength, ionic strength of a particular solution is put into the glass capillary, and therefore you have this capillary, the solution inside it, a conduit which is coming out, and then the end which is a plug with maybe polyvinyl chloride polymeric resin with the ion exchange material trapped inside it. So, this can give all properties of what an ion selective electrode would essentially need. The reference electrolyte which is filled inside can vary depending on what analyte of interest is being measured using this particular electrode. Okay. So, when we talk about the various MEMS modules for electrodes, the basic idea in MEMS is that whatever is being done by the conduit can be transferred onto a microchip level, and some of these electrodes essentially can be screen printed onto these chips rather than just hanging plain wires. Like for example, if you look at this particular chip here, and this is again an excerpt from lab on chip as a paper reported in lab on a chip for measurement of exocytosis processes in single cells essentially, and this is also an excerpt of a work that had been earlier done in our group. So, if you see here, these are screen printed electrodes on a silicon wafer which can be easily fabricated using this microfabrication strategies that we have been talking about before, and there are these small positioning channels, these narrow small positioning channels between these sensing electrodes, and two reservoirs essentially on both sides here, and so there is a flow of cells and positioning of cells over these individual channels or electrodes, and the ion exchange resin here can be coated, spin coated selectively using photolithography on certain specific areas where these electrodes interact with the solution of interest, okay, and can be rapidly recorded using a DAC system, a data acquisition system, and so all the electronics can be built surrounding the particular chip here of interest, and this can be a bio-MEMS device to measure electrochemistry of a single cell. Okay. So, how do we fabricate some of these devices to make the positioning of the cell? It is very interesting that you basically make a channel here in this particular form in a silicon in a manner that is shown like this. Okay. So, this essentially is the top elevation of the device. So, you have a cell reservoir on one side, these are all microscopic features, and you have a transportation channel which is blocked here at this particular end. Okay. So, this channel is blocked in one end and emanating out of the cell reservoir, and there are these docking stations, these small 15 microns by 15 micron docking stations in silicon which can dock a cell like this. Okay. And following this, there is a small channel, a very small channel which is lower than the size of the cell, but can essentially flow the fluid which is carrying or transporting this cell to this docking station. So, if you look at this whole assay on the side view, this is essentially where the cell would go and dock, right, and this is the small dam which is able to connect both sides, that means side 1 and side 2 on this device. So, this is the waste channel side. Okay. The waste channel side is similarly positioned. Okay. So, if you see the waste side, you find out that the waste side also has a channel emanating from this waste reservoir, and it goes and stops or gets blocked all the way here, and there are connecting channels in between the main flow channel and the waste channel in this particular manner. Okay. So, the cell comes here, docks itself, and the solution which carries the cell is able to move from this particular dam area into the waste area. That way the fluidics is made continuous, the fluid flow is made continuous. So, the fluid comes like this, goes into this area because it cannot go ahead anymore, because it has a blocking here, there is a certain pressure here, and it comes and positions the cell and moves out into the waste reservoir, something like this. But then we can actually make the docking station of the size of a single cell. Okay. So, therefore, if it is 15 by 15 microns and we assume the diameter of this particular mammalian cell to be about 15 microns, this is what happens. You have these cells here kind of docked in these docking stations, and the electrodes, the platinum working electrodes, are placed just about the docking position, and here you can give the ion exchange resin in form of a coating, so that whatever happens to the cell or whatever releases happen from the cell through its ion channels can be easily gauged using this platinum electrodes through this ion exchange coating, which can be given on the membrane, which can be given on the top of the electrode here. Okay. So, this is a fantastic example of how an electrochemical device can be fabricated from a MEMS platform to more towards a MEMS platform. Thank you.